Welcome to my presentation. My name is Solt Kovacs. I'm working at ETH Zurich, and today I'd like to talk about on what we call optimistic search strategies. So this is about change point detection without full grid search. This is joint work with Hausen Lee, Lorenz Hartner, Axel Munk, and Peter Willmann, and the draft will be available on archive within a few weeks. So change point detection in general considers the following setup. You have some observed ordered observations. And then the initial distribution F1 changes at some unknown time point to distribution F2, and then maybe some other points to further F3, F4, etc. The goal is then to estimate the number and estimate in particular these locations of the change points. So a very classical setup is where these distributions F1 through Fk0 arise from normal distributions with differing means, but variances that are constant and observations that are independent. So this would be kind of, you have observations here and then a jump, let's say up, and then maybe another jump up, down, something like this. Okay, so this very classical setup has been studied in the last decades, and in recent years there is more and more work on change point detection in multivariate or high dimensional setups. This poses several challenges, and today I'd like to focus on a new algorithm that helps to speed up computations massively in such complicated scenarios. So let's look at the motivation with a single change point. So how do people usually search for a single change point? Well, you could split after second, after third, fourth, etc. observation, and at each of these split points, one could fit a different model on the left-hand side and a different model on the right-hand side, and then see how much better we are by fitting these two separate models compared to just fitting one model on all of the data sets. So this defines for each split point what we call a gain. Okay, so what's the problem? The problem is if you're in such a complicated high-dimensional scenario, then each model fit is expensive. I mean, such a graphical lasso or let's say random forest. And if you really fit on each possible split point, one of these models, then it quickly becomes computationally infeasible if T is large. So the question raised was whether this is necessary, and the answer is no. Our optimistic search strategies that I described only need the logarithmic number of evaluations. Okay, so let's look at an example. So what we aim to do is to find the maximum of this black curve. This is what we call a gain curve. And if you evaluate this gain curve at all of the 2000 split points in this example, you need roughly 1200 seconds. As opposed to this, we only need 2 initial starting points and further 14 adaptively chosen split points for the naive optimistic search. And thus we roughly need only 11 seconds, so we have a speed up of factor 100. Okay, and why is this the case? So why is this with the full grid search so expensive? Because we have a high-dimensional Gaussian graphical model that is changing. The true change point is here in green, and we need at each split point the graphical lasso fit. So if we fit many of them, it becomes computationally, well, at least very demanding. Okay, so how does the search exactly work? Well, we start with 2 initial split points at 1/3 and 2/3 of the observations, and we compare the 2 gains, corresponding gains. So here the left one is higher, so we tend to believe that this left-hand side is more interesting. So what we say is, okay, let's throw away the outer right-hand side. And now just focus on the remaining left-hand side. Then let's say we choose another split point and then compare again the 2 gains. In this case, this gain here is a tiny bit higher, so we tend to believe that somehow this right-hand side is more interesting. So let's just throw away this left side. And we do this similarly. So actually, how do we choose always the new split point? Well, we keep one of the previous ones, and the previous one defines a left-hand segment and a right-hand segment. And we say, okay, let's take the longer one, in this case it's the right-hand one, and put the new evaluation point in the middle. Okay, so this is how we obtain, in this case, number 2. So once we get the new split point, what we do is again the same. So we just compare the corresponding gains. In this case, this one is higher. So we keep the left-hand side and we say, okay, let's throw away this outer right-hand side. And we do it in similar fashion. In this case, we would keep the left-hand side and throw away this. So as you see, we very quickly narrow down the search and kind of climb up on this peak. So we end up here with 14 marked in blue. And it's actually a tiny bit off from the global maximum that is just besides the true change point marked in green. But if you look at the overall picture, it's not too bad. So we get fairly close to the global maximum. Okay, so as a summary, I propose an iterative procedure where at each step I add, so I have one split point from the previous step and I add one more, a new one in the longer segment in the middle, and then I compare the gains, and depending on which one is higher up, I throw away either the outer left or outer right hand side. Okay, so in terms of a picture, let's say we search here and we already narrowed down the search to this segment and we have a previous split point. Then we add the new split point in the middle of, in this case, this longer segment, and then either this is higher than the previous split point, then we would keep the right hand and throw away the blue area. If this is lower than the previous one, then we would do the opposite. So then we would throw away the red area. And I'd like to mention that this search itself is similar to golden section search that has been proposed earlier on. Okay, so here's it formally if you would like to look at it later. And the question now is whether we can come up with any guarantees for this procedure. And the answer is if you have a population or let's say noiseless case, then if you have a single change point that would correspond to a unimodal function, which is smooth and has a single peak. And in that case, this naive optimistic search that I introduced would find a global maximum logarithmic number of steps. But of course, the question is what happens in a noisy case, which is not smooth, but rather like a very wiggly version, as in the first example that I showed you. So for this, let's consider this classical univariate constant change in mean setup that I introduced earlier, now with a single change point and the cumulative sums of Q-sum statistics as a gain. Then, as a result, we have that this naive optimistic search is consistent, but only if the ratio of shorter versus longer segment is not too unbalanced, meaning that the change point cannot shift asymptotically too fast, too close to the boundary. Okay, so the question is, can we improve on this? And the answer is yes. We have an advanced version with a slight tweak. And the tweak was motivated by Liu and co-authors, as well as by seeded binary segmentation, the proposal we had earlier on this year. So what we do here is we investigate first a preliminary set of split points at dyadic locations. So basically we consider split point 2, 4, 8, 16, etc. until reaching T half, and the same on the right hand side. And we check which one of these has the maximal gain, and at that location we define suitable neighborhood, and only in that neighborhood we do naive optimistic search. So if we do it this way, then actually for a single change point we get minimax optimality even. So this is quite surprising, because what it means essentially is, so what one has to note is that this set has cardinality that is also logarithmic. So in total, also this advanced search has a logarithmic number of fits and steps. So what is surprising that even though we only do a logarithmic number of fits, as opposed to the full grid search, which needs t fits, we are also minimax optimal. So essentially, asymptotically, we lose nothing compared to full grid search, which goes through all the t points, even though we only do a logarithmic number. Okay, so here's it formally. And the question now is whether or what to do with multiple change points. And here we can rely on many techniques, such as binary segmentation, or our own proposal of earlier this year, seeded binary segmentation. So this seeded binary segmentation is similar to wide binary segmentation that many of you may know, but it's considerably faster than wide binary segmentation. And this optimistic version thereof is even faster, And what we obtain is even minimax optimality for multiple change point cases. Okay, and if you consider binary segmentation and optimistic version thereof, then the nice thing is that it needs typically number of change points times logarithmic number of model fits. So kind of the computational time is adapted to the number of change points, and it's only off by a logarithmic factor. The problem is that in some very special cases, this search might fail due to some signal cancellation effect. But these are kind of very rare. And in this paper, Lonchin and co-authors, in very complicated high-dimensional scenarios with missing values, it still performed very well empirically. So in terms of theory, it has some special cases where it doesn't work unless one modifies slightly the procedure. But in practice, it works very well. So overall, multiple change points are more challenging, but combinations with the existing techniques are possible, and they have differing pros and cons in terms of computational times and theoretical results. And there are further phenomena that one could for sure study. So overall, this optimistic search that I introduced, especially the advanced version thereof, has very strong asymptotic guarantees. So for a single change point, one essentially loses nothing compared to full grid search, even though we only do a logarithmic number of fits. We can extend to multiple change point cases, and due to the very few number of evaluations of the gains functions, we are very fast. And this is helpful mostly in complicated high-dimensional scenarios where model fits are expensive, such that we would like to avoid fitting too many models. Okay, so in terms of simulation results, I don't have time to show it, but what one would obtain is similar to the first visual picture that I showed you, that we get orders of magnitude faster, and in terms of estimation error, we are not too much worse. Okay, with that, I'd like to conclude. Thank you for your attention, and here are the references.